And so our next talk will be by Morin, Brunet, Merril, Painter, Ochoa, and Castro. Preliminary metamorphic PT paths for the Manhattan and the Hartland Schists.
Hi, so I'm Adrian. I'm a assistant professor of geosciences at Wellesley College.
I'm Katherine. I'm a geoscience and math major. And I'm a junior geoscience major. I'm Scout. I'm a sophomore geoscience and chemistry major.
I'm Aiyana. I'm a sophomore geoscience major.
And I'm Emlynn, also a sophomore geoscience major. Today, we're going to talk about preliminary metamorphic PT paths for the Manhattan and Hartland schist. Before we go into our results, I'll explain a little bit of the tectonic setting of New York City to give you some context. So the bedrock of the Bronx and Manhattan is thought to record metamorphism and deformation associated with the closure of the Neo-Iaptus Ocean and the eventual collision and accretion of the tectonic island arc onto Laurentia during the tectonic erosion. From the bottom of the stratigraphic column to the top, we have the Precambrian Fort of Gneiss, which is topped unconformably by the inwood marble, which is then overlaid by the Manhattan schist and the Hartland schist. The Manhattan and Hartland schists are separated by a thrust fault known as Cameron's line. The Manhattan schist is thought to be sourced from Laurentian-derived sediments, while the Hartland schist is thought to be derived from the tectonic arc. This would make Cameron's line a fundamental terrain boundary or suture. This is a cool model. Adrian will talk to us about why it may not be that simple.
Yeah, so again, this is a really cool idea. We have this fundamental suture terrain boundary running through the Bronx and Manhattan, but most of the story appears to be based largely on correlation with units elsewhere in New England, and not so much on the detailed petrochronology of the rocks themselves. And as Steven and Nick and others showed in 2020, we can't even really agree on where Cameron's line might be in the city. And this map shows multiple different locations for Cameron's line in the Bronx and Manhattan. And so as metamorphic petrologists in a metamorphic geology lab, we wanted to apply our toolkit to try to solve this problem. And so we had two questions that we're interested in. The first is trying to define the conditions of metamorphism in the Hartland and Manhattan formations and explore the nature of Cameron's line. So if we stick with the general hypothesis here that Cameron's line is this fundamental terrain boundary between these Laurentian-derived sediments and tectonic arc or dashwoods, if you're Paul Carabinos-derived metasedimentary rocks, we would expect to see at least two major features. We'd expect to see a metamorphic break across the thrust here, so deferring metamorphic conditions, different pressure, temperature, time paths, and we'd expect to see deferring detrital zircon signatures. So we're going to focus mostly on the metamorphic story today, but if you're interested in the DZ, Steven has some really cool hot off the presses data that he'd, I'm sure, be willing to talk about. So we're going to look at two samples. We're going to start with CRT06, which is a metapelitic member of the Hartland schist. It is from Katona Park, which is, I don't know, 12 minutes from my old high school. And we'll talk about MAT 2017-01A, which is a metapelitic member of the Manhattan schist in northern Central Park. And so we are looking at a hanging wall sample and a footwall sample. And Katherine will get us started on the petrography.
So first, for CRT06, this is a Hartland schist sample of garnet, kyanite, sillimanite, biotite, muscovite, plagioclase, and quartz. The matrix is defined by well-foliated biotite cross-cut by late muscovite. Garnets are typically about 1 to 2 millimeters in diameter and subhedral, often replaced by muscovite and sillimanite rims, and contain an inclusion assemblage of quartz, plagioclase, ilmenite, and zircon. The aluminosilicate textures in the sample are of particular interest, and we see kyanite occurring in two habits. First, as subidioblastic porphyoblasts in the matrix that are up to 200 microns in length. And second, as a nodule of nodules of randomly oriented grains with interstitial muscovite and plagioclase pseudomorphed by fibrillite. So we have the nodule outline here in orange and the pseudomorph outline in green. We interpret these kyanite pods as recrystallized leucosomes via the reaction of muscovite, plagioclase, and quartz to melt in kyanite. Sillimanite likely grew at the expense of kyanite during exhumation and associated melt recrystallization. Now, to place this petrography into context, Izzy will explain thermodynamic modeling.
So we created pseudosections with the program GIBS using the MNCKF MASH TI system and the SPAC-18 thermodynamic dataset from Severe in Wolf 2022. And pseudosections show the stable mineral assemblage for our bulk composition over a range of pressure temperature conditions. So we have pressure increasing on the y-axis and temperature increasing on the x-axis here. And the purple line here shows the garnet isograd, where we start to see garnet growth, and the blue line shows the melt-in isograd, where we start to see melt. And important fields are colored in here. And coupled with the petrography Katherine just covered, we ultimately deduced this pressure temperature path of CRT06 represented by these black arrows, which I will be discussing. So first, our light gray A1 field shows the garnet inclusion assemblage constrained to around 550 to 600 degrees Celsius and 4 to 8 kilobars. Next, our A2 peak field here, given the presence of kyanite in leucosomes, is constrained to about 750 degrees Celsius and 8 to 11 kilobars. And lastly, our green A3 field is our final equilibrium assemblage at around 650 to 800 degrees Celsius and 4.5 to 7 kilobars. So altogether, this produces a clockwise PT path with garnet growth at lower amphibolic faces, Merril and heating to kyanite grade conditions, and isothermal exhumation into fibrillite stability, and continued exhumation to our equilibrium assemblage. And to introduce our second sample, Scout will discuss its petrography.
So the next sample we're looking at is MAT 2017-01A, the Manhattan schist from Central Park. This sample is a garnet kyanite sillimanite Manhattan schist. Its matrix fabric is defined by biotite and cross-cut with late muscovite. There is notable kyanite and sillimanite. We'll return to aluminosilicate textures, but first we want to focus on the garnet petrography. So in thin section, we saw it was around 1 millimeter in diameter and typically subhedral and rimmed by muscovite and biotite. And we looked at garnet zoning specifically. Here we have major element WDS maps where the hotter colors are higher counts. And these garnets preserve growth zoning, which was really important for us to deduce their PT paths. We can see that iron, magnesium, and calcium all increase in concentration from core to rim, while manganese does the opposite and decreases. So we used intersecting isopleths to understand their PT conditions. And then the aluminosilicate textures of this sample in outcrop, they can actually appear as centimeter large nodules called boot grabbers. And in thin section, they appear as randomly oriented, less than a millimeter long nodules with interstitial, muscovite, and plagioclase. And similar to CRT06, this is interpreted as a recrystallized leucosome reaction. Sillimanite occurs in two habits here. One is blades cross-cutting kyanite, and other is fibrillite needles included in late muscovite. And again, we believe that the sillimanite likely grew at the expense of kyanite during exhumation and melt recrystallization. So to place this sample into context, we did thermodynamic modeling, which Aiyana will explain.
So this is just like our last pseudosection where we have pressure increasing on the y-axis and temperature increasing on the x-axis, showing the stable mineral assemblages for a bulk composition, but with the addition of garnet isopleths. So here the garnet compositional isopleths are shown as solid lines for the core and as hatch marks for the rims. And first up, our light gray A1 field is constrained by the garnet core isopleths, which define a broad intersection at around 550 degrees Celsius and between 4 to 6 kilobars, which is right on the garnet isograd. Second, and is evidenced by the kyanite leucosomes in the thin section, just noted by Scout, this pink A2 field is limited to about 700 to 750 degrees Celsius and 7 to 11 kilobars. We can also note that kyanite is a paratectic product in all of these samples. And then lastly, our light green A3 field is constrained by the tightly intersecting near rim isopleths at 700 degrees Celsius and 6 kilobars, which is in the sillimanite field. So we're seeing this sort of same clockwise pressure temperature path as before, with a slightly steeper slope, maybe due to the overthrusting of Hartland. So we're going from these lower amphibolite facies, garnet growth, then burial up to kyanite grade anatexis, isothermal exhumation into fibrillite stability, and continued exhumation to equilibrium assemblage. And next we have Katherine, who will conclude our analysis and take us home.
So lastly, we're going to compare the pseudosections here, and we have the Manhattan sample in the hanging wall and the Hartland sample in the footwall of the thrust fault. And we see similar clockwise PT paths for both samples, suggesting similar PT histories. The Manhattan sample is currently better constrained, but given our current data, the metaphyletic samples of both the Hartland and Manhattan tell the same story. So let's recall our guiding motivation and hypothesis. To show Cameron's line is a fundamental terrain boundary between Laurentian-derived and tectonic arc-derived metasedimentary rocks, we needed evidence that there is a metamorphic break across the contact, but we did not find this. In our comparison, we saw that samples from both schists experienced similar PT histories with minor differences in peak pressure. This lack of metamorphic breaks suggests that Cameron's line is not actually a fundamental terrain boundary. Instead, it may be a pre-distant metamorphic thrust fault that juxtaposes different stratigraphic units of the Laurentian margin.
And so we're continuing to work on this problem. We're going to include some more detailed microstructural analysis to sort of add deformation to our pressure temperature paths with Nick Roberts at Hamilton, and include some detailed monazite, zircon, and garnet Sumerian Ingenium petrochronology with Jay Thomas at Syracuse and Ethan Baxter at Boston College. And ultimately, we want to constrain robust pressure, temperature, time, deformation paths for the Manhattan Hartland formations and all of their compositional subdivisions, like the Bronxy type or Pelham Bay type, so on and so forth. And just as a little sneak peek here, here is a yttrium L-alpha map for a monazite from CRT06. And we can see two age domains, a younger tectonic, I guess with an error age, and then an older, more interesting 540 age. Okay, thank you specifically to the Central Park Conservancy and the New York City Parks Department and the Bronx Zoo, and then a whole host of folks that have spent a lot of time talking to me about anatexis and luminosilicate reaction textures. And we'll take any questions.
That was awesome and also perfectly timed. I've never seen such a collection of people give a talk that was so smooth and ended on time. That's awesome.
I mean, I will, you know, I didn't put them in acknowledgements, but this work is driven by undergraduate research students here at Wellesley, who've really been doing a lot of the fundamental petrography. That's the groundwork for all of us.
Do we have any questions for the group?
I have a question. First, that was a really beautiful talk. That was beautifully organized and orchestrated. I found it amazing. I'm not that familiar with the geology of this region, but if it's a terrain boundary, I would think that would be also based on evidence from a lot of other places. So is your conclusion that it's a fault, not a terrain boundary, raise issues about other regions in the eastern United States?
It is actually kind of a parallel thought. So there are a lot of folks led sort of by some of the USGS folks and Bob Winch who's now at Westland, sort of reevaluating what's supposed to be Cameron's line in southern Connecticut as they're sort of remapping. And they're seeing a sort of similar story. What we might consider Cameron's line, at least in southern New England, doesn't seem to be the same as the suture up in Canada, right? The Red Indian line, which has pretty drastically different detrital zircon signatures on the other side, as Paul and Carabinos and others have shown, and differences in metamorphic histories. So I think in southern New England, which I'm kind of lumping New York into, which hurts me as a native New Yorker, but it is what it is. I would say we are sort of reconsidering what Cameron's line means for the regional geology.
Thanks.